Good morning. Welcome back. In the previous session, we discussed the multi-channel filtering for multiple removal. And today, we'll continue on this topic, talk about more effective ways to do the multiple removal. So session 6 is noise removal. In this session, I will talk about 3 parts: noise, tau p transform, and the parabolic radon transform. Multiple is one type of noise. In general, we consider seismic data have signal and the noise. Anything you want to keep is a signal. Anything we do not need at this stage, we call noise. Maybe this noise can be used in the late stage. For example, if we separate the multiples from the primary, in the modern days, people try to use some multiples as a useful information to enhance the seismic migration result. So in that stage, the multiple becomes a signal. Nevertheless, we do need an effective way to separate multiples from the primaries. So in summary, any required energy we consider as a signal. In the reflection seismogram, there are mainly primaries. Anything else, including the multiples, we consider as noise. Noise, in general, can be classified into 2 types. One is incoherent noise, such as random noise. One feature of a random noise is the white spectrum. Every frequency components have almost same magnitude, so it's white spectrum. Another feature in coherent noise is unpredictable. In contrast, the coherent noise have 2 features. One is repetitive, and another one is predictable. For example, for multiples, we have a fixed time period. So multiples is a predictable coherent noise. For coherent noise, I list 6 examples here. In any acquisition, marine or land seismic, you do have a direct waves. Direct waves are coherent between traces. So this is coherent noise. Surface wave, which in the seismic community we call the ground roll, is coherent noise. You have a clear trend in the waves between traces are coherent. Air waves is also a coherent noise. Reflection here, in this case at the moment, we treat it as a coherent noise because our purpose is to generate the subsurface reflection image, reflection image. But sometimes reflections are useful information, for example, for static processing. static is to investigate the near surface layer velocity variations around the spatial coordinate. So both the depths of the water layer and the weather layer and the variation of velocity around the layer varies. So that's, in that sense, that's coherent reflections becomes a useful information, right? So just I would like to repeat coherent noise or signal. Some depends on the different situation. Near surface scattering is also a coherent noise. We have a clear trend, lasts for a number of traces, but we don't need it for when we try to generate a subsurface image. Traffic is, if we have a seismic line next to a trend line, so the train track may have a regular sources. So we do looks like have a coherent signal, coherent source, generate waves, but this is not what you want. You want to get around that. So there's noise. This one example here. That's a shot together from land seismic position. We clearly mark it as the low frequency wave trend here as a ground roll. So when the wavelet is fat, which means the dominant frequency is lower, so we call the lower frequency trend, right? So this is the ground roll, and at the point 5, that's the signal. This weak signals, but coherent. There are reflections. My question is why at a zero offset there's a time delay. We usually assume your source receiver at the same position, your chop time will be 0, but here we do not, right? We have a time delay. Anybody know what happens? What sort of acquisition geometry? Or this shot together? You think about a straight line of receivers along the x direction, but your source is not on the same line. We have a x offset. So the source is outside of a receiver line. In this case, source outside the receiver line. So x in x direction offset is 0, but actually in y direction it's not 0. But you have time delay. And it is evident from this ground roll. Ground roll starts from a source point, but from the actual source point to the x equal to 0, there's a distance, you see that? So this distance actually tells you how far away your source from the receiver line. This is a marine data set at 1.2 or 1.3 second. There's a water layer, water bottom refraction, and the double that at 2.6, we have a first order multiple, 3.9 have a second order multiple, and then so on and so forth. Right? So that is a typical coherent noise water layer multiple. So the wave bouncing up and down many times within the water layer. Here is another example from marine acquisition. The deeper water, the water bottom refraction at 1.7 or 1.8 second. On the corner here, there's direct waves. Right. So between the direct wave and the first arrival, which is the water bottom reaction, there's something arrived earlier before the water bottom refraction. This could be, again, the solidity effect. So source receiver may be on the same line, but as aside of the acquisition line, there's a side effect. There's something like a material area in the subsurface, in the water, have a strong reflection from the side, and then your line receive that before the water bottom reflection. So that's another example of a coherent noise here. So USO stands for unidentified seismic objective. Unidentified seismic object. Noise attenuation in the acquisition. We did learn that before. Number of methods. For random noise attenuation, we use the bandpass filters to get rid of low frequency, either ground roll or high frequency random noise, or get rid of the notch or use a notching field to get rid of the industrial electricity frequency. Web-size correlation is also an effective way to get rid of random noise. The web-size correlation is use your signal, which is a frequency sweep, to correlate to the recorded data. So by correlation, you effectively reduce the random noise. The example we saw before, after the correlation, the reflections gradually appears. If without correlation, without the sweep correlation, the raw recording data, you do not see reflections clearly. Vertical stacking is another concept. Vertical stacking means at the same position, you have multiple receivers, multiple geophone, multiple hydrophone, and you sum them together based on the linearity, based on the time invariant. You can increase the strength of the signal, meanwhile reduce the noise. Of course, CMP method is one of the methods in the field. The CMP in the field here really means you should make effort to maximize the fold of CMP. The fold means the number of traces allocated to same CMP, same common midpoint. So number of traces per CMP point. We try to generate the redundant information for further processing. For coherent noise, grouping is one of the effective way in the field for reduce coherent noise. Typically, it can help to suppress the horizontal components, so the ground roll or any other horizontal components. For example, the wave travel within the water. So grouping is an effective way. Grouping means in a seismic data, single trace is not recorded by a single geophone or single hydrophone. It's recorded by a group of phones, group of hydrophones, group of geophones, and based on the linearity, you sum them together. CMP method, of course, also effective for coherent noise. After NM stacking, the parameters will be enhanced, but the coherent noise, such as multiples, will be suppressed. Not completely though, typically for neural set, but NMO nevertheless is a good way for coherent noise reduction. Noise attenuation in processing. For random noise, we can use bandpass filters typically for high frequency random noise. Vertical stacking is also the effective way for random noise attenuation. CMP gather, we learned that after NMO stacking, for N traces, CMP stack will reduce the random noise energy to 1 over square root of N. 1 over square root of N, so reduced by square root of N. N is number of channels per CMP default. So in order to effectively reduce the random noise, we should increase the number N from field acquisition. That means we try to generate redundant information for the noise attenuation. FK filtering, here I show you one example based on the predictability. If anything predictable, we keep it. If not, we just consider as a random noise. So this forward backwards really means we have in 2D case for the central trace, this should be predictable from left-hand side to this trace or from right-hand side to this trace, right? So the forward backward predictable. If we extend this to 3D, there will be fxy filtering. In fact, it will be 360-degree azimuthal prediction. For single trace, you can predict from 300-degree azimuthal directions. Coherent noise deduction. Coherent noise reduction from processing. Deconvolution is one of the powerful tools. We learned that for deconvolution. It is a single channel processing. We do deconvolution trace by trace. Although nowadays people study to use coherency between multiple channels, among multiple channels. So develop the multi-channel deconvolution, try to have a more stable deconvolution operator. Deconvolution is the inverse filtering. Filtering is equivalent to the convolution. Deconvolution means inverse filtering. CMP method, enamel stacking, is an effective way to reduce the coherent noise. We already said it before. Last week, we tried to use FK transform to separate different coherent events in the FK domain based on the deep information. Today, we'll learn two methods. One's called tau P transform field. One's called parabolic radon transform field. So similar to FK, tau P and the parabolic radon, they are the two transforms. Explore the different feature of a coherent event. In general, the seismic data set is displayed in the T and X domain, which is T is time, and X could be the offset, could be the receiver position, could be the CMP position. Nevertheless, this is called just distance. Right? So in general, seismic data is the TX domain. FK domain, we do the two-dimensional Fourier transform. One Fourier transform is done with respect to the time. Another transform is done with respect to the space position. So that's two-dimensional. So in the FK domain, we can separate different events according to the dip. Because dip is the inverse of velocity, so we can also say the separation based on the velocity. Right? In the FK domain, as we said, we can based on dip or velocity to do filtering. The dip is measured by how many seconds time delay within the certain distance. So delta T over delta X. If delta X is a trace interval, this gives us units of second per meter. If we ignore the trace interval, just simply say how many millisecond time delay per trace, effectively you assume delta X equal to 1, right? So in the FK domain, you use the ratio of K over F to memorize this formula. You simply use a trick here to check the physical unit. On the left-hand side, the unit is meter. Left-hand side is second per meter. On the right-hand side, the wave number is circles per meter. Frequency, tempo frequency is hertz, which means circles per second. So circles cancel by circles, so you end up second per meter. So this is the way to memorize that. In the FK domain, all the linear events, all the dip will go pass through K equals 0 point. So this is why we call the generally FK domain field as a fan field based on the different dip. In the processing domain, we measured 2 domains, Tx domain, which is original data domain. Fk domain, we based on the dip, we can decompose the seismic data from Tx to the different events with a different dip in the Fk domain. Here today we're talking about 2 transforms, tau p and the parabolic radon transform. Tau p is something in between Tx and Fk. In the Fk domain, the dip defined by wave number and the frequency, right? So in the tau p domain, tau is effectively T, so we only use a dip here. But this dip will be variable as a function of time. We exploit this dip as a variable of a function of time to do the filtering. And the parabolic radon will follow not a dip, but a curvature of a parabolic curve as a function of time. Dip events, the curvature for dip events is 0, but dip angle. So the third one depends on dip angle. The fourth one here depends on curvature. That's the difference. Topic transform. Topic transform in other field is called radon transform. Radon transform is invented by this gentleman, Johann Radon, Austrian scientist. And we, in the seismic community, we simply call it tau p transform. We'll see why. And we will keep the radon transform for the next session specified for parabolic radon transform. We call it radon transform. But for the general radon transform, linear radon transform, we call it simply tau p transform. It is an integral over the data space from a negative infinity to positive infinity. That's in theory, right? And some integration in the discrete form is a summation. So this is stacking along different dip, along different angle. So this is also called a slant stack. And any event will be described by a dip. And here, P really means dip. As a function of time, time is tau. Tau is the interception time for any linear event at x equals 0. The time is called tau. So you can see that tau p transform is a halfway between Tx and Fk. It is equivalent to applying a linear move out, rather hyperbolic move out, and a stack with a different velocity. So that's the difference. Linear move out, rather hyperbolic move out. Let's see how to implement. On the left of the panel here, let's see the blue lines. Blue lines have a constant dip, P1. So from top to bottom, all the blue lines have a same dipping angle, P1. And On the middle panel, the blue vertical line here is P1. So follow this blue line, you sum all the energy together and put the total energy into the position here, interception time. So it's tau P. The next line, sum them together, put the P here, tau here. This is tau P. Tau really means the interception time for each of the individual straight line. That's tau. P is the dip of this curve, just lines. And for different P, P2, you have a P2 here. You do the identical thing. You sum all the energy along the straight line, and you put the total energy into position tau. So this is a tau P trace. That's one way. So you use the constant P, scan all the data, and put on top left. This is one way to do that. Another way to do that, for individual tau, which individuals interception time, use a different P, use a blue P, red P, or you sum all the lines in, and put this sum of the value into the position tau P panel. So the tau is the corner here in this case, the interception time, but all the different P's, different lines, different dip. And then you do after that, you do second position, you do the same thing, and so on and so forth, right? So there are two implementations for the tau P transform. One is on the left, one's on the right. These two implementations have identical efficiency. Either use a constant P or use a constant tau. You end up the same tau P transform result. There's no difference. This is the physical meaning of a tau P. Tau P, P here is sine theta over velocity along the surface. So that means this line of source in the air, here the horizontal axis is on the surface, right? You have so many sources. If they short same time, you have a flat wavefront. So this is plane wave, okay? But if they have a delay time, or effectively they have the short same time in the air, but when they travel to this surface, at a different time, so basically have the wave look like this. This wavefront. That T is measured by the distance here, and then the P, which is Rayleigh parameter. We were familiar with this ratio here. This Snell's follows the Snell's law. Rayleigh parameter is constant following any ray path, following a single ray path. Doesn't matter how complicated the subsurface is, how complicated the travel path is. Rayleigh parameter is a constant for along a single ray path. So what we can do, if we cannot, of course we cannot, short all the shots in the air, you can do is you short this shots along the surface with time delay. So that's time delay given to you here. So this one, compared to this one, you have the certain time delay. If you have a shots delayed by this time, you effectively have the plane wave. Plane wave means you have a plane wavefront. So tau p, in terms of physical meaning, is a plane wave decomposition. It simulates a line source. A line source instead of a point source, individual point source, simulates a line source. And measures energy in one direction, perpendicular to the wavefront, and the wavefront is flat. Right? So P is conserved in the propagation. As I said, the P is constant flowing rate path. A physical experiment for the plane wave experiment. As we said, we cannot have a simultaneous shot in the air, but we can have delayed shots on a surface, the accurately calculated delay, and this wave in the subsurface will be mimic plane wave propagation. Tau p transform in the other fields called the radon transform. Here, I'll give an example. In the ordinary coordinates x and y, you acquire along this line. Right? You can transfer it to the radon transform domain with the angle, which is theta here, and the radius. So this line can be transferred to the radon domain to be a dot. So here is the angle, and here is the distance from here perpendicular to the line. That's it. And then you do summation along this, and a dot here. That is a radon transform. Here is an example. You have two lines in the xt domain. After the radon transform, the image is in the theta and rho space. That two lines become two dots. You can see the straight line in the tx domain becomes a point in the radon transform domain. These two lines become two dots. If you isolate these two dots, that means you can effectively suppress anything outside of the two lines. Further example here, the same two lines that have a strong noise. You can see these two lines becomes two dots here. And if you somehow preserve these two dots and then do the inverse radon transform, you get rid of all the random noise. That's an effective way to improve the signal to noise ratio of the image. That's the radon transform. And in the seismic community, typically for data processing, we do not use the angle and the distance, but we use intercept time, tau, and the dip, p. So we just straightforwardly call it tau p transform.